Welcome, geologists, and we're here to learn about unconformities, and then we'll be looking at marine facies. Terms you may not know yet, but by the end of today, you'll definitely understand these. So if you look at these pictures and see this particular place, I want you to imagine, why does this red not continue on? You can see these angled beds right here, right? They shouldn't just abruptly stop like that. In geology, they should pinch out, or if they've not, then they've been kind of cut off. And they've been cut off right here, and kind of see this little wavy line? That tells me a clue that we've worn down some of these rocks and they're missing in the rock record. That is called an unconformity. Specifically, you're looking at an angular unconformity. So we're going to take a second to show you how one of these things can form, so you kind of have a perspective due to an animation of how this process works. Because if you understand how they kind of form, then you can have a better idea of what we're talking about. Here is an animation of how an unconformity forms. So let's start with, we've got a basic seabed at the bottom of the ocean. I'm going to lay down some flat sedimentary rocks. So notice they've been laid down in their flat horizontal position, like the law of original horizontality states. So they get tilted and squashed. We know that happens after they're deposited, right? The next step is I'm going to begin to wear them down. So they were there to begin with. Now we're missing part of those rocks. The next step is I'm going to put brand new sedimentation on top of it, creating brand new sedimentary rocks. So those are new and flat, so we're missing stuff right here. There's a universal line that occurs in geologic maps or block diagrams that's a wavy line, or it can be done in a red block line that represents some missing time. So we should have one right here. Let's show you what happens if we erode some of this stuff away. Once I erode some of that away, I'm for sure missing some rock record. So where'd it go? It's been eroded away. This section was eroded away, at least the brown rocks were, before the gray was ever put on. So we actually had two situations occur here. We lost some of this first, then we lost some of this. So how do you recognize this in the field? That's what our lesson is about today, so let's get started. So let's define an unconformity. It is a break in the rock record sequence. In other words, you're missing some of the chunk of time that should be there in the rock record in sequential order, but some of it's just not present. It's like it got taken away. And in geology, we have to use that as a clue to help us interpret what was going on for that rock to have disappeared or never to have been created at all in that area. So you've just watched an animation on how unconformities form, and I'm going to kind of apply that to this thing right here. So these were the seabed layers that were laid down in your animation. And then we get new rocks on top. In this case, it's a mountain. So it squashed the smithereens out of this. Well, this mountain's going to take a while to wear down. When it does, it gets down to sea level again. And here we got a dinosaur hanging out. And this stuff, he dies, and these rock layers are worn down some more. And then we come in with a new ocean and put some new rock layers above it. That's exactly the kind of thing that you saw in the diagram or the animation that you just observed, and also the same kind of situation that you saw in the first picture that I asked you to interpret. So this black line right here represents some missing time. In geology, usually this is a wavy line, and or it's a block line like this black one or a red one. So what causes an unconformity to occur? There are two basic things that you need to know. The first one I don't think is as common, but sometimes we have a period of non-deposition. For whatever reason, we don't have enough rock to weather and erode to create great volumes of deposition to make rock layers. So that can be circumstance number one. Second circumstance is more common. This is where you're going to get a massive amount of weathering or erosion of a rock layer that was deposited, and then it's missing in the rock record. For example, this section of the Grand Canyon right here is called the Great Unconformity. You'll be learning a lot about that in a minute. But the squiggly line, here's that wavy line I was talking about. This would be an unconformity. By the way, I see another squiggly right here. This would be another unconformity. Different kind. I see one over here. Another one indeed. So what we're looking at is some missing time at each of those locations. In this case, especially with the schist, the granite, and the schist right here, we're looking at a gigantic missing time, to be exact about 1.2 billion years. And when you look at this segment right here, between this one and this one, that is a huge amount of time as well. It's still that 1.2 billion years. You're like, well, how did that happen? Well, that's the story. And that's what we look for as geologists, is the story in the rock. So this is that same diagram, but in a picture. This is the Grand Canyon, and so this was the stuff at the bottom, that was the schist and the granite, and this was the sedimentary rock laid directly above it. So this would be a special type of unconformity referred to as a nonconformity. But we're going to define each for you and show you how they form. There are three basic types that you need to be familiar with: an angular unconformity, a disconformity, and a nonconformity. Something to jot down in your notes. Angular unconformities and disconformities. They have something in common. They involve sedimentary rocks at the bottom beneath the unconformable contact, which would be the wavy line, and then there's sedimentary rock above it. So that's the key, sedimentary rocks on both sides of the unconformable contact. Not the case for nonconformities. You'll have igneous or metamorphic at the bottom, overlain by new sedimentary rocks on top. So the unconformable contact has something different at the bottom as opposed to sedimentary. So let's get busy and show you the three different types. The first one is an angular unconformity. You're already familiar with this one. This is what the animation showed. This is what the first picture of our lesson showed. This type of unconformity has sedimentary rocks at the bottom that have been tilted or deformed. And you can see that you got a special type of feature. Our next lecture series, we'll talk about this right here, what this is right there. It's actually called an anticline, and this would be called a syncline right here. So these used to be flat, and now they've been bent and folded. Here's just some tilted sedimentary rocks, but notice that they don't extend indefinitely until they pinch out. Instead, they've been kind of cut off, chopped off at the top. That happened because of an erosional process. And once we eroded them down, we brought in a new set of rocks and laid them directly on top. Same situation here. So we got sedimentary rocks on both sides of the angular unconformity, or that wavy line, that represents missing time. So how did we form one? Just the way you saw in the animation. We built layers A, B, C. We tilt them, and as soon as they get tilted, rocks tend to have issues. They tend to weather faster. Then we're going to come in and lay down some new rock layers, F and G, where you're like, what the heck happened to D and E? Don't know. Maybe they didn't get laid down here. Maybe they did, and we have no rock record left of them. So if that's the case, C is much older than F, and we have some missing time there. That is what the angular unconformity would be. Here's a classic unconformity. This particular angular unconformity is famous because of James Hutton, the father of modern geology and the father of the rock cycle. This is a place in Scotland that he recognized and described as understanding that this must have taken an immense amount of time to create the rocks themselves, then certainly to wear and weather them down and erode them down, and then lay new stuff on top. So this is a famous location in Scotland that is kind of where he first described unconformities. Let's get to unconformity number 2. I think this is the hardest to recognize because all the rocks are stacked on top of each other like a set of pancakes. So disconformities, I like to give them a nickname, the disappearing act unconformities. So I'll tell you a story, see if you can relate to it. It's Thanksgiving afternoon. It's the afternoon in time for football. You put your favorite game on, right? You got all these leftovers, and it's 6 or so in the evening. It's time for a snack. So you go into the kitchen, you get your turkey and your ham, you make your sandwich, and you get distracted, and you got the sandwich open, like on a plate. One half is on open, with the meat and cheese on it, and you got the other half to start putting whatever stuff you're going to put on the other side. You get distracted, and the dog's over there in the corner, and he spies it, he sees it, he checks it out. Without you seeing, while you're distracted, the dog comes over there and snatches the meat and the cheese off of your sandwich. You go to close it, not even realizing that the meat and cheese are missing, right? And you go to take a bite, you're like, well, what's up with the sandwich? What happened to it? You had a disappearing act. Well, that's kind of the way that disconformities work in the field, except it didn't happen after the sandwich was closed. It happened before the sandwich ever got a chance to be closed. That meat and cheese got eroded off, and then the second half of your sandwich got put on top later on. That's what we're looking for in the field. So you get flat sedimentary rocks like you see here, and then you get some missing time. So this would probably represent some kind of a river basin, because river basins make a V-shaped profile like you see here. This one right here is going to be more in tune of a glaciated environment, more than likely, because you kind of got blocky sides with the flat U-shaped bottom. And so this would probably be caused by glaciers. But nevertheless, it really doesn't matter which and how they formed at the bottom. What matters is I got flat sedimentary rocks on top. So you might be wondering, how would you recognize a disconformity in the field? That's an excellent question. Usually by fossil content, specific rock type. These are all clues that you have to recognize. So out of the three, disconformities by far are the most difficult to recognize. So let's make a disconformity happen. I lay down layers 1, 2, 3, and 4, but I uplift this whole section in some kind of mountain building event. And then I wear down layers 3 and 4, and now I'm just left with the two oldest. So here's your erosional surface that represents the boundary between 2 and 3. Later on, I bring in a new situation like a new ocean, and now I've laid down layers 6 and 7. Obviously, I'm missing layer 5. Okay, so did it happen in this area, or was it eroded away? Likely, it was eroded away. More than I would put my money on it. That's probably what happened, but we're not 100% sure. But we do know we're missing time, at least with layers 3 and 4. And you might go, well, how did I even know if 3 and 4 were there if they're not in this picture right here? We have them nearby. That's a good rule of thumb when you're looking at unconformities, is you look at a regional perspective of the rock layers that are common in an area. So here would be an example of a classic disconformity. I've got Cambrian aged sandstone right here. Directly above it, I've got some Mississippian aged rock. So in your chapter 1 of your textbook, there's a geologic time scale. You need to get that out and find it. It's towards the end of your chapter. And when you find Cambrian, I want you to notice how many periods are missing between Cambrian and Mississippian. So it goes Cambrian, Ordovician, Silurian, Devonian, then Mississippian. So if that's the case, I'm missing 3 periods of geologic time right there. That's a significant gap in time. So again, how would you recognize that without noticing that there's a distinctive difference in the rock texture here? Fossil content's usually your best key. Here's a disconformity in the field right here in Texas. You've got some Permian aged rock that's about 270-ish million years old right here, overlain by about 66 million year old rock right here, maybe 80 million year old rock. Regardless, there's a gap, right? So this would be your unconformable contact. Both sides of these are sedimentary, and they're both parallel to one another. That qualifies it as a disconformity. So this is the disappearing act right here. Just use the sandwich example, you'll get it right every time. So what's the nonconformity? It's the abnormality of the 3. It's the strange one. My personal favorite, because they're just kind of neat. They have a different kind of rock at the bottom, igneous and or metamorphic. And oftentimes you can find igneous and metamorphic rocks side by side in the field because of the way metamorphic rocks impact, especially igneous rocks. So typically a nonconformity represents an immense amount of missing geologic time. Why? So I'd like you to think about, let's say, the Smoky Mountains, which is in the Appalachian Mobile Belt. The Smokies have a lot of intrusive igneous rock and metamorphic rock inside of the cores of that mountain range. While they've been heavily weathered down, most of them have sedimentary rocks on top. So these would represent the cores of mountain ranges. Not always, but most of the time. I could get a circumstance where I just get a little dike that's come up to the surface. I've worn that down and there's some new sedimentary rock in its place. Usually it's big picture stuff when we're talking about nonconformity. We get some kind of a big core of a mountain range. So let's reflect back to the Great Unconformity, where I was showing you the bottom of the unconformity of the Grand Canyon. It was made out of this stuff right here. So there was a big giant mountain that used to exist there back in the Precambrian that got worn down before the new sedimentary rocks in the Cambrian started to get deposited right on top. To be exact, there's about 1.2 billion missing years. That's rather impressive. So how do you make this? IM stands for igneous or metamorphic. J stands for Jurassic period. K stands for Cretaceous. So I've laid down, and I'll put an age to this. Let's just call this IM. We're going to make this Devonian in age. You got that time scale handy. You can see where that is in the Paleozoic. So I'm going to put that there, and later on, Jurassic and Cretaceous get put there. Notice there's a irregular surface here too, so what that tells me is I'm missing rock in consecutive sequence between this igneous and metamorphic rock, Jurassic and Cretaceous. Nevertheless, I'm going to wear down Jurassic and Cretaceous in a mountain building event, and all I'm left behind is this Devonian age stuff right here. What's up with that, right? So later on, I bring in what's called Paleogene. Some of you may know that as tertiary age. That's going to be from about 66 to 65 million years old up until about 2.6 million years old, where the Quaternary starts. So right here, we are definitely missing a massive amount of time if this is Devonian and this is early tertiary, which would be somewhere around 66 million years old. So that's important to recognize in the field. Again, how would you know that? You would have to age date this or have a relative age of the bottom rock, and then you could certainly look at fossil content between the two to determine what kind of age rock this is right here. Probably not going to find fossils very well on the igneous or metamorphic just by the type of rock that they are, but I guarantee you this limestone right here, you're going to find fossils more than likely. Here is a nonconformity in the field. I've got igneous rocks down here overlain by some flat sandstones on top. So this used to be the root of a mountain range. It would be this stuff right here, some kind of an igneous pluton, and it got worn down and then flat sedimentary rocks on top. Here's another nonconformity. This is the actual Great Unconformity at the bottom of the Grand Canyon. First of all, notice this irregular surface right here. That is your nonconformity or your unconformable contact. And this stuff right here is much, much older than this here. This is about 1.7 billion years old. This is about 542 million years old. So remarkable difference. So when we're thinking about the Great Unconformity, you have to realize there's over a billion-year gap between the rocks that are down here that are igneous and or metamorphic, because there's both cases in the Grand Canyon. And then you get the flat sedimentary rocks directly above it that are Cambrian in age. So you're looking at your time scale in your book, you're like, but they're in sequential order in the book. They may be, but the gap of time is substantial because the age of this is much older than the age of this. So we're missing some rock in between. That's the story. Where did the rock go? This is that same location that you saw in the sign in Colorado. So the Great Unconformity does not just exist in Arizona where the Grand Canyon is. It's prevalent throughout different parts of North America. So this is actually Box Canyon in Colorado, and this is the igneous or metamorphic rock overlain by the flat sedimentary rock. The gap is about 1 billion or more years right here, 1.2 billion to be exact. Here's that same look. So the Depete sandstone is the oldest of the Paleozoic aged rocks in the Grand Canyon. So it age dates somewhere between 550 to 542 million years old. If you're looking at your book, it starts around 542 million years of age. So this stuff sitting at, let's just make it a nice even number, 550, just so it's easy to do the math. And the Vishnu schist that's touching directly beneath it is 1,700 million years old or 1.7 billion years old. So you take 550 minus 1,700, and you're going to end up with about 1,200 million years of missing time. That's equivalent to 1.2 billion years. So you have to imagine this used to be the core of a great giant mountain. Specifically, the first supercontinent that ever formed, called Rodinia. So kind of exciting stuff when you start to realize, wow, there used to be a big giant mountain in the Grand Canyon. Where is it now? We still have proof that it was there. We got the Vishnu schist, and it's still really, really thick. But this thing was a lot bigger back in the Precambrian. It took that long to wear it down and then bring in a sea level that would put in brand new stuff right on top. So which one was the Great Unconformity we saw? Is it this one? Is it the middle diagram? Is it the right diagram? I realize you don't know rock symbols yet, but you're fixing to know them, and it'll really help you interpret this. So we know it can't be this one, because this has sedimentary rocks on the bottom that have been tilted and sedimentary rocks on the top. I think you've eliminated this one probably, because they're all parallel. So this would be your disconformity, your angular unconformity. This is the nonconformity, which would be the same thing you just saw in the Great Unconformity. So let's see how good your memory is and kind of go over the different unconformities we just learned. What is this type of unconformity? I have igneous or metamorphic rock overlain by flat sedimentary rock. You're like, well, that looks like what we just saw in the Grand Canyon. You're right, it is. This is a nonconformity, specifically the Great Unconformity. You have igneous or metamorphic overlain by flat sedimentary. An irregular surface here. You named it, it's a nonconformity. So we get flat sedimentary rocks above and tilted sedimentary rocks below. What would this be? It is definitely an angular unconformity. Before you're quick to judge if it's angular unconformity, you need to find out if it's tilted sedimentary rocks that have been metamorphosed or if it's just tilted sedimentary rocks. In this case, you were correct. It's tilted sedimentary rocks. Here I've got igneous granite down here overlain by flat sedimentary sandstones above it. What type of unconformity would that be? Like, gosh, it's another nonconformity. Well, it is indeed. They're very common. What type of rock is this or unconformity? You're like, well, duh, that's an angular unconformity. You are correct if you said that. This is definitely sedimentary shells right here, overlain by flat sedimentary looking like conglomerate or breccia rock on top. So definitely a angular unconformity. We got two kinds of unconformities going on in this picture. So you've got metamorphic or igneous rock down here, overlain by these pancake rocks right here, which are sedimentary. So what type of unconformity is that? You're like, well, again, it's a nonconformity. And it is. This happens to be the Great Unconformity in the Grand Canyon. But way up here, at the very top, you can see the character change of this rock to way up here. We get another unconformity. At the very top, we begin what's called the red wall limestone, which is Mississippian in age. And that's a completely different rock age than these sedimentary rock layers right here. So you would have a disconformity in that case if there was an age gap between these rocks and the rocks directly above it. So what kind of unconformity is this? Like, oh, that's funny. It's kind of a weird thing, isn't it? This is a geologist's sense of humor, a jack-o'-lantern, but what kind of unconformity did they try to make here? And it is definitely an angular unconformity. You got tilted sedimentary beds overlain by flat sedimentary beds. This would be a perfect place to take a break. I'll see you back for the second half of Marine Facies in just a little bit. Bye.